acceleration due to gravity. His mass I gave to you, that's 70 kilograms. The acceleration due to gravity, we're talking about if I take an object near the surface of the earth and I let go, what is the rate at which the velocity changes? What is the acceleration of something that's falling? So this G right here stands for acceleration due to gravity. And it is approximately 9.8 meters per second squared. So in the absence of air resistance, an object that fell, its velocity would change by 9.8 meters per second every second.
It would be that for every one, right? It's always gonna equal that.
All right, so let's talk about always there. Always doesn't quite apply. G depends upon where you are, this little g. On Earth, it is approximately 9.8 meters per second squared. In Winston-Salem, it is 9.798 meters per second squared. Now, the reason we know this is that there have been studies, at this point they've done the entire world, but a while back they were actually finding out the value for acceleration due to gravity, and the sensor that they had, if you look out these windows right there, there's this road that comes in and hits Silas Creek. Right there in the median, basically, if you continued on that road where that median is, that's where they had the sensor. It is about the same level as where we are right now. So if you're looking at the labs and they say, sometimes they'll say, let G equal 9.798 meters per second squared, that's because of that. Now some might say 9.796, that's because I made a miscalculation and hadn't looked at the data properly. That was my mistake. I've corrected a lot of them, no guarantee I've corrected all of them. Let's talk more about the variety of little g here. And it is a lowercase g. Uppercase G has a different meaning. There we go. The smallest one I actually found, Mexico City. So G of Mexico City is 9.779 meters per second squared. Gravitational acceleration due to gravity in Winston-Salem, 9.798 meters per second squared. Death Valley had the highest that I found. Death Valley, 9.8344 meters per second squared. To give you some sense of the variety over the surface of the Earth. And I've got various other countries throughout the world, and they fall in between that range right there. So 9.8. Now, if you look at the entire world average, it's 9.806 something. And so some textbooks will say use 9.81. You see that popping up. In a lab, never use 9.81 meters per second squared for G in a lab. Unless you happen to be somewhere else, but if you're doing it here, don't use that. Hewitt just rounds it off and says use 10. He uses 10 a lot.
So what do we have to use?
If I don't specify 9.8 or 10, in a lab, I'm not doing your lab, but in a lab, oftentimes I ask you to do that. Because that's an actual value for real life situation. On the Quizzer test, some students will use 9.8, some students will use 10. Unless I specify, I'm fine with either. All right, so the weight of the person is whatever 70 times 9.8 is, and if someone be kind enough.
686.
686. And the units?
It would be, would it just still be, oh, it would be Newton?
There would be units.
No, newtons.
Oh, newtons, yes, it is newtons.
Ooh.
Sorry, I'm the third.
No.
Now, if you look at straight up, if I'm looking at this and I multiply those units, I actually right here have a kilogram and a meter over second squared. There's my kilogram, there's my meter per second squared. And so my units really are kilogram meters per second squared. However, at some point, the powers that be said, you know what, we're gonna call that a newton. A newton is what is known as a derived unit. So a newton, by definition, that's why there's 3 lines there. It's not just equal, it's equal because it has been defined this way. A newton is a kilogram meter per second squared.
In this problem right now,
Well, newton is always a kilogram meter per second squared.
okay.
But that's why I can multiply kilograms times meters per second squared and end up with a newton in the end. And for those a little bit shakier on the math notation, it can also just as easily have written it as kilogram meter over second squared. It means the exact same thing. So I imagine the 3 lines are probably new to a number of you. The 3 lines, like an equal sign, means that it is by definition. So this we now know is 686 newtons.
So what were we calculating? I thought we
His
were-
weight, we're finding out what his weight was.
Oh, to be able to find the.
Yeah. And I realized a mistake I just made. That 1200 newtons, let's go ahead and make that change now while we're here. This 1200 newtons, let's make that 600 newtons.
So this is what the problem started with, would just be 600, not 1200.
That 1200 means that this side over here is actually gonna be pushing down and that thing is out of line.
So just disregard 1200.
Disregard the 1200, write down 600. That was, I made a silly math error. All right, so his weight, 686 newtons. To give you some idea of size, my weight is about 1,000 newtons. Okay. If he is in equilibrium, the total force acting on him is 0. If he is in equilibrium, what is the normal force acting up on him? I heard somebody say it quietly. Or not. I thought I heard something.
86? I don't know.
Did you say 86?
Yeah.
Where'd you get 86?
686 minus 600.
Oh. No, don't subtract the 600. That 600 is acting on the beam. I'm looking at him. So now that I've isolated it, what is the normal force acting on him?
I don't know.
686.
Yeah, 686. That's I thought I just missed the 6 when you said it the first time, the first 6. If he's in equilibrium, the force is up equal to forces down in magnitude. So the normal force is 686. So this number right here is 686. I am assuming he's not bouncing on the beam. He's standing there, trying not to fall. Or throw up. Now we come down to the beam. I have 600 acting up here, I have 686 acting down there, and I have the weight. Let's figure out the weight of the beam. The weight of the beam is mass times acceleration due to gravity. The mass, I said, was 30 kilograms. Acceleration of gravity, 9.8 meters per second squared. $294. looking really cluttered over there. Let me sort of clean it up a little bit. I got my beam right here. I know I have 294 newtons acting down. I got 686 newtons acting down. I have 600 newtons acting up. And then I've got something else over here. This is the problem. Cleaned up. It's in equilibrium. The force is up equal the force is down in magnitude. What's the total force acting down?
600?
It's not that.
Do you add it?
Yeah. Well, the total force acting down, just add them up. Is that 980?
Yeah, 980.
Yes, yeah, all right. So I have 980 newtons acting down. Therefore, what has to be the total force acting up?
980.
Absolutely. I know where 600 of it's coming from. Therefore, what's left over?
380
Finish it off.
newtons.
There's the answer.
So how did you get that?
Total force up equals the total force down. I know I have 980 newtons acting down, so I have to have 980 acting up. 600 is here. This is whatever's left over.
Okay.
I'm going to connect this to something we did last week. Any questions before I solve it slightly differently?
I was writing. How did you get 980 newtons?
Those are the two forces acting down.
So you just add them together?
Yep,
Alright, cool. Thank
they're in
you.
the same direction.
And the two forces acting down for the void, for the command, and the main.
Correct.
And normal doesn't need a subscript?
No, because there's only one pair of normal forces. If you wanted to put subscripts, it's not wrong. Not necessary.
And with the equilibrium, you said the forces have to equal each other, or?
Equilibrium means the total force down in magnitude. Magnitude of the total force down equals the magnitude of the total force up.
Okay.
All right, let me do it slightly differently. No, sorry, Clay?
So, why doesn't the weight equal the mass? What's the difference? Why don't you weigh the mass? How's that?
All right, so mass is not location specific. My mass is about 100 kilograms. If I went to the moon, my mass is still about 100 kilograms. Mass depends on how much stuff is inside me, and that's the official term, stuff. The weight is basically a gravitational pull. And so that is dependent upon where you are. I weigh about 220 pounds here. On the moon, I would weigh about a sixth of that. So my mass doesn't change, but the amount of pull on me does. And so that is one of the differences between mass and weight. Weight is a type of force, mass is not. Is that sufficient?
Yes, but.
Okay.
I forgot how you got 294.
That was the weight of the beam. I did the mass of the beam times, which was 30 kilograms, times the acceleration of gravity, which is 9.8.
So on the test, if we wanted to just try and keep our numbers pretty and just use 10, that'd have been okay?
Yeah.
Okay.
Why didn't you use 10?
Because oftentimes in physics, some instructors and some textbooks go, you know what, the ideas are complicated enough. Let's just deal with simpler numbers and try to see if they understand how to do the problem. And so they said 9.8 is close enough to 10. That's the reasoning of why 10 is often used. But again, it's one of those things, if you're designing a bridge, you better not be using 10.
Okay.
Although for bridges, you probably can get away with it, because they have so many, what are called factors of safety thrown into it, that the difference probably gets washed out, but
If we times 70 by 9.8, we're gonna get a decimal, right? Would you mark it wrong if we put a decimal down?
alright. On quizzes and tests, I usually pretty relaxed about that. On labs, well, I'm not doing your lab, but on a lab, I would care.
Right.
But quizzes and tests, I'm grading quickly, I'm going, yeah, I had 686 and she had 685.3, yeah, good enough. There, rarely will somebody get that close having done it completely wrong.
So it doesn't matter either way. you know, what I'm saying.
No. You're trying to convince me that you know what you're doing, and, putting decimal places in, usually it's a matter of personal preference. It doesn't, for some people, it just doesn't feel right not putting them in. And that's fine.
So we can use 9.8 or 10.
Yeah,
Okay.
yeah.
C8 bigs.
Yeah. Sig figs, what fun they are. It's primarily a chemistry thing.
Yes.
All right. I'm gonna do this slightly differently from this point right here. Connecting with what we did before. I know that the total force is 0. I know that because it's in equilibrium, and that's part of what equilibrium means. The total force is 0. I'm gonna let up be positive. Why? Why not? I could have made down positive just as easily. This unknown right here, I'm just gonna label X because I have no imagination and I'm using X for the unknown. So X plus 600, because it's going up, minus 294, minus 686 equals 0. That's the math problem we're working with here. Conceptually, it's the forces up equal to forces down, or the total force, taking direction into account,